Welcome to my presentation about lighting with Unity. In the next 30 minutes, I will show you several techniques to light an environment, from standard rasterization with light maps and probes, all the way to ray tracing and path tracing. I will use the High Definition Runner Pipeline, or HDRP for short, which is tailored for high-end applications. This is going to be our ugly starting point, without any global illumination or GI for short. We will use the Sponza Atrium. It is a famous building in computer graphics because many engineers use it to test GI systems. I will show you the whole process to generate the GI, and I will cover 4 main techniques. The first technique will be baked light maps and reflection probes. These are typically found in games or low-end devices. In the second step, I will introduce our new adaptive probe volume system, which is an automatic grid of probes that capture the irradiance. In the third part, I will cover the ray tracing pipeline and talk about real-time ray traced reflections and GI. Finally, we will look into path tracing, which is the holy grail when it comes to lighting quality and ease of use. My name is Pierre Yves. I'm a senior technical art manager at Unity. I lead a team specializing in all aspects of graphics. I worked on several high-end titles during my time in the game industry. First, I will cover the basics of HDRP. I will show you how to tune the sky, the sun, and the local artificial lighting. To start with, let's cover the volume system. It is the main way to control the visual settings per camera in HDRP. Let's add a box volume and place it in the center of the atrium. I can easily change the bounds of the volume with the dedicated handles. All the volume properties will be stored inside a profile asset on disk, which means multiple volumes can share the same profile. Let's add a color adjustment override, and then I can add a contrast and a saturation override. As the camera enters the volume, these settings are applied to the frame. I can also set the mode of the volume to global, and the settings will be applied to my scene regardless of the camera position. The weight lets you control how much the volume affects the camera. I can also adjust the blend distance to control how far from the volume the overrides will start to be applied. This volume system is really a core functionality of HDRP. You can use it to adjust the sky, the fog, the exposure, the post-processing, etc. The sky will have a huge impact on the indirect, diffuse, and specular lighting. It will also dictate the lighting ratio in the scene between the shade, the sunlight, and all the other artificial lights. To set up the sky, we're going to use the volume system. This is done with a visual environment override. So if I move above the atrium and then disable the fog, you can actually see the HDRI unobstructed. I can choose between 4 types of skies like none, HDRI, gradient, and physically based. Exposure is going to be crucial as it controls the intensity of the sky. I can also set the illuminance of the sky directly using an arbitrary lux value. Of course, I can also adjust the rotation of the HDRI. So let's go back to the atrium and see how the sky impacts the scene. I'm going to clear all the baked lighting data. This way you can see that in the absence of proper indirect lighting, HDRP will always fall back to the sky probe. That's why using the right exposure is so important, because it will impact the general look of the lighting. Here are common exposure values for skies. If you own a lux meter or even a smartphone, you can do your own readings. For our scene, we use a value around 14.5 EV, which corresponds to a clear sky. Let's talk about the sun and the artificial lighting. As I move the sun around, you can see that there is no bounce lighting yet. HDRP is physically based, so we control the color temperature of the light using the Kelvin scale. For this scene, I will use the daylight preset at 5500 Kelvin. I can of course change the illuminance of the sun in lux and use the daylight preset at 100,000 lux. Now let's have a look at the sun shadows. Without them, the light will obviously leak in the whole atrium. We use a technique called shadow cascades, which allow for greater shadow resolution near the camera. In the shadow override, I can change how far from the camera the cascades will be rendered. To preview them, let's toggle their debug view. Let's use a lower shadow map resolution to make the difference between each cascade more obvious. The first cascade gets full resolution, the second one gets half, and so on. To hide this difference of resolution, HDRP offers cascade blending. If I disable it, you can see that there is no soft shadow transition between cascades anymore. You would typically see these hard transitions in video games and on lower-end devices. Finally, let's have a look at the artificial lights. I can input an intensity in lumen manually, or use the interior preset at 1000 lumen. Units can be candelas, lux, or EVs. Our light doesn't shine very bright, however. This is because the ambient sky probe leaks all over the place and competes with the artificial lighting. We can tune the indirect intensity with the indirect lighting controller. It lets you multiply the indirect lighting for the active camera. And if you don't use or can't use any form of GI, it can be a quick way to dim that unwanted ambient lighting. However, this is not the proper way to generate GI for this scene. And we've completed the intro. We've seen how the sky and the direct lighting are set up, and how the sky probe is used as a fallback for the indirect lighting. Now we can finally start our journey into global illumination, or GI for short. We'll cover baked light maps and reflection probes. Light maps are textures that store the lighting. They are very cheap at runtime, but take time to generate. To generate light maps, we will use the lighting window. Tick the Baked GI checkbox, select Baked Indirect, and pick the Progressive Lightmapper. You can then customize sample counts and denoising options. I use a resolution of 25 texel per unit, which also means 4 centimeters per pixel in the light map. For objects to participate in the GI computation, you need to tick the Contribute GI in your mesh, and make sure that they all receive their lighting from Lightmaps. You can give more real estate in the Lightmaps to certain objects as well. To speed up the bakes, you can disable the Always Refresh function, so that most GPU resources are allocated to the light bake. We can now press the Generate Lighting button to produce the light maps. Now we have to wait. Hopefully for us, it's going to take under a minute. However, depending on the size of the scene and the number of samples, it may take several minutes, if not hours. The light maps are starting to converge. Near the end of the process, the light maps are getting denoised, compressed, and stored as EXR. As you can see, the results are not great yet. There is a blue and green tint on the materials. With the rendering debugger, you can see that the scene still reflects the sky entirely. But we can fix this specular leaking using an object called reflection probes. So what are reflection probes? They are objects that can capture the surrounding environment into a cube map. The cube map is then used to provide specular lighting to the nearby objects. Let's add a reflection probe in front of the camera. This is a baked reflection probe by default, and as you can see, its gizmo is a black sphere at the moment. Once baked, it has successfully captured the surrounding environment. Now I will need to place more reflection probe in the scene to capture correct local reflections. Updating the bounds, the capture point, and the fade distance on the edge of the probe is a time-consuming task. Hopefully for us, I already have several reflection probes in the atrium. As I activate them all, you can see that the scene is finally looking as expected without specular leaking. In this environment, I have 13 probes covering all parts of the atrium. They are placed in a way to minimize their number. For instance, these pillars share the same lighting condition, therefore they can share the same reflection probe. Whereas this probe at the back is constrained to dark area, to limit the amount of sunlight captured by the probe. The optimal way to place them depends on the correctness you're after. The more probes, the more exact the reflections, However, this will have a memory cost. Let's override again our material to set them as mirrors. The reflection resolution isn't very high. However, for a scene with mostly rough material, this is perfectly adequate. The reflections are also projected based on the camera position within the bounds of the reflection probes. This is a cheap way to ensure the reflections are more or less connected to their surrounding. All in all, the results are much better compared to the sky reflection fallback. Now that our scene is lit correctly, we can cover the complex topic of camera exposure. As we've seen earlier with the sky, a correct exposure is extremely important for the photorealism of the scene. So what is exposure? It is simply an amount of light. A high exposure means a lot of light, for instance 14 eV for a sunlit environment. A low exposure means a low amount of light, like 4 eV for a darker interior. Then in photographic terms, it means the amount of light hitting the sensor of the camera. You can check the exposure formula below with f-number, shutter speed, and ISO. These are parts of the exposure triangle. If you are not familiar with these camera terms, don't worry, we do provide presets. To demonstrate how easy it can be to set up the camera exposure with HDRI, I've used this real photo taken with a Nikon D80. When I apply the same aperture, shutter speed, and sensitivity to the physical camera in Unity, I can get very similar results. Of course, the 3D assets don't exactly match the real-world counterpart, but in terms of illumination, if you squint your eyes, the results are extremely close. Let's have a look at our correctly tuned scene. If I look at a very bright patch, the camera will expose for this area automatically. Then if I look at a darker part of the atrium, the camera will brighten the frame. When correctly tuned, the exposure system works like a real-world camera that adapts dynamically. To understand how to set the exposure up, I will first use the fixed exposure mode. This area is lit by the sun, so it's going to use 13 eV. You can also pick the preset for a sunlit scene. Then the problem comes when I look at a darker area, because the camera still exposes for the sunlight. This area will appear too dark as a result. So I need to manually lower the exposure value to about 6 to 8 eV for this area to look appropriate. But now, if I look back at the sunlit area, it is overexposed, nearly white. To solve this conundrum, I need to use the automatic mode instead, and make sure limit min and max are within this 6 to 13 eV range that we know works well for this scene. As I look at a darker area, the image brightens towards an exposure value of 6, and as I look back at the sunlight, the system will crank up automatically the exposure towards 13 eV. By the way, we also provide interesting debug views for the exposure. For instance, here we have a heat map showing the distribution of exposure values in the frame as well as the clipping. Now we've completed the first part. We have a well-lit static environment that receives GI from baked light maps and baked reflection probes. And like a real-world camera, Unity can automatically expose the scene. In part 2, I will cover the lighting of dynamic objects that cannot rely on baked light maps because they can move in very dark or bright parts of the scene. Therefore, they need to be lit by a different type of lighting provided by light probes. We will first look into the legacy light probe group, then I will introduce our new adaptive probe volume system. First, let's see how dynamic objects are lit by the legacy light probe. When I move this dynamic object in the atrium, it does pick up some odd lighting from the environment. The received indirect lighting doesn't feel grounded, and it changes uniformly as the object transitions between dark and bright areas. Let's see where this lighting is coming from. If I select a light probe group, you can see that there is a network of probes that capture the indirect lighting. This network is set up by hand, and the artist will need to place every probe manually, which can be very time-consuming. Usually the probe needs to be placed around areas of high lighting contrast to capture as much lighting variations as possible. So as I move the capsule, it will sample the 4 nearest probes to the pivot of the object, compute a blend of the lighting based on proximity, and apply the result of this blend to the whole object. This solution is very efficient on mobile, as the lighting calculations are extremely cheap. However, it is not great visually for high-end scenarios. So let's swap to our brand new adaptive probe volume system, and as I move the dynamic object, the lighting remains perfectly stable, and it receives many lighting variations on its surface. If I increase the length of the capsule, it still receives correct per pixel lighting, something the legacy system cannot provide. So you can see that the entire world is populated automatically with these probes, with very little to no user input. If I zoom out, you can see that the scene is still within the bound of the probe volume and is subdivided automatically. We use a sign distance field of the geometries to do so. Based on the subdivision settings, the system will attempt to place a higher density of probes near objects, whereas empty spaces should receive less probes to reduce the memory cost. To control globally how probes are placed in the world, you can use this dedicated tool. There you can control the min and max distances between probes. We'll actually move this tool back into the lighting window in the next major release of Unity to centralize the workflow. Here you can see in more details how the scene is subdivided and how probes will be distributed. Now that the user doesn't need to manually place any of these light probes, it is a huge time saver compared to the legacy system. However, the problem with automated probe placement is that probes can sometimes end up inside objects and create invalid lighting data. This can produce light leaking, especially when dealing with high contrast lighting. However, our system can automatically mark probes within objects as invalid, like the ones between floors and inside pillars. We also have a virtual offset that will slightly move the probes in case they are inside a geometry or too close to their surface. With the debug view, you can see how much the probes have been nudged before the irradiance was captured. In this scene, the probe volume shows very little to no sign of light leaking. This means artists wanted to spend a lot of time fixing light leaking problems. Now we know that probe volumes are great for dynamic objects. Let's see if they can also replace light maps for static objects. Let's load another scene only lit by a probe volume without any light maps. You can see that the difference is quite minimal at first. Obviously, there might be a slight lack of occlusion and contact shadows around the pillars, but this is expected from a probe solution that interpolates between fixed lighting capture points. I will clear the baked data and rebake the scene to show you how quickly the probe volumes can be baked. We are literally talking about a handful of seconds for this whole atrium. The speed and the flexibility that probe volumes provide is fantastic compared to light maps. Just the fact you don't have to author lightmap UVs is great for artists. If lightmaps are better in some areas compared to probe volumes, you can simply tag the corresponding meshes to be lit by lightmaps. Or you could increase the density of probes by reducing the minimum distance between them. Here, light maps are better suited for capturing the occlusion under the arches, whereas the probe volumes are not because of their sparse distribution. This is where screen space or ray trace ambient occlusion can be used to fill the gaps. I've mentioned previously that the probe volume offers some leak reduction features. First, we have the normal bias, which simply pushes the lighting along the surface normal. We also offer a view bias, which nudges the lighting along the camera vector. This is surprisingly effective. Finally, we have an automated mode that fixes most harsh leaks. It uses the probe validity as well as the orientation of the normals. It does a great job on the walls and floors at the back. Here's a comparison of the 3 systems presented so far. Lightmaps offer the best quality overall for static objects, but the baking times are long. Pro volumes are not far off visually, given how quickly they are baked. However, they have a more interpolated look. Typically, they will lack strong contact shadows and micro-occlusion. However, for real-time scenarios like games, they offer a highly scalable alternative to Lightmaps. Legacy light probes, on the other hand, are really not fit for purpose in this scenario because they do not offer per-pixel lighting. In this part, we have set up the environment using the brand new probe volume system. The results, although not comparable to Lightmaps, are good enough for many scenarios with minimal light leaking. And there is little artist overhead in terms of asset authoring or scene setup. Now that we've covered most rasterized techniques, let's look into ray tracing. The render pipeline still uses rasterization techniques for the rendering, but we can replace certain inputs by their ray trace counterparts. That's why we call it a hybrid pipeline. HDRP offers many ray traced effects, but for this presentation we will focus on ray trace reflections and ray trace global illumination. The techniques we've covered so far rely on the baking of the lighting data. So if the sun moves, the indirect lighting is not updating properly. Thankfully, you can use ray tracing to have real-time reflections and global illumination. First, we can use the HDRP wizard to make sure that the project is set up correctly. Then, in your project settings, select your active render pipeline asset and make sure the ray tracing is on. Make sure as well that the property called maximum light per cluster has a high enough value. Otherwise, some light-related objects might not be included in the ray tracing, and you could end up with light leaking or light popping. First, let's look into ray trace reflections. On these three mirror spheres, you can see that the reflections are of very low quality. They also don't update when the lighting changes. This is because they receive their specular lighting from baked reflection probes. To get real-time ray trace reflections, we will add an override to our volume. The results are now much better. However, there are some issues at the back of the atrium, behind the camera, with light leaking and a lack of shadows on certain assets. First, we're going to tune our light cluster to ensure it covers the whole atrium. To preview the light cluster, we can use the corresponding debug view. You can see the cluster is a collection of wall space axis-aligned cells centered around the camera. Each cell contains a list of lights that will be used for ray tracing. This cluster should cover all the geometries you want included in the ray tracing. Then to fix the missing shadows, we will tune the ray tracing settings. First, we can extend the shadow curling to ensure correct shadowing for objects outside the viewport. And we'll also set the shadow fallback to black to fix potential shadow leaking behind the camera. You might notice that the reflections are a bit dull. To fix this, we can increase the clamp value. However, the denoiser might struggle with higher values, especially on rough surfaces, because the range of the signal to clean up will be much wider. We provide two modes for the reflection, quality and performance. Although more expensive, we'll stick to quality for this demo. A very important setting to control performance will be the minimum smoothness. This controls which pixel will receive ray trace reflections based on their smoothness. A lower minimum smoothness will greatly increase the cost of the rendering, as more pixels will require ray trace reflections. The rest will fall back to much cheaper reflection probes. You can even disable screen space reflections per material to avoid any unnecessary cost. The max ray length is also important. You want to minimize it for performance reasons, yet you want to ensure the rays are long enough to hit every part of the atrium. The beauty of this system is that you can change the lighting radically and reflections will be updated accordingly. However, as we still use baked light maps, the bounce lighting doesn't update yet. For that, we will need to activate ray-traced global illumination. So let's add an override for ray-traced GI, or RTGI for short. First, you can notice that the effect is not very intense. As we've done already for the ray trace reflections, we will increase the clamp value to maximize the effect. You can see that the indirect lighting becomes immediately more intense. But again, it might make the work of the denoiser more difficult. Now, if I were to move the directional light, you can see that the GI updates in real time. If I move to the corridor upstairs, you can see now that the sunlight propagates nicely in the environment, on the ceiling especially, after the sunlight hits the floor. And then as the sun disappears, you're left with a dark environment. The big advantage of RTGI is that it is fully dynamic, something static light maps are not, obviously. Artists will often prefer a tool that provides fast iteration time rather than a slower, inflexible tool. Here you can see a comparison between ray trace GI and light maps. In the central image, more bounces can provide a slightly stronger indirect lighting. On the third image, the baked light maps will still produce the best lighting overall. However, light maps lack flexibility and they can have very long computation times. Ray tracing, on the other hand, can produce adequate bounce lighting in just a few milliseconds. We've now completed the third part. We have a fully ray-traced environment with ray-traced GI and reflections. And the results are great for dynamic scenarios when the lighting can change quite radically. Finally, I can cover one of the most exciting developments for real-time graphics lately, which is path tracing and its denoising. It is a technique commonly used in films and high-end visualization. To activate the effect, we'll use again the volume system. You can now see that the path tracing is in action in the viewport. I'll increase the maximum intensity returned to boost the indirect lighting. It's going to take a few seconds for the image to clean up, and the results might still be noisy afterwards. To solve this, we've recently added AI denoising with either the solution from Intel or NVIDIA. Thanks to denoising, I can now radically lower the number of samples. So with a couple of samples, the results are very painterly. But as I increase the number of samples progressively towards 50, I can eventually get a very clean image after a few seconds, with near perfect lighting and no aliasing. Whenever the camera moves, because of the noise, it's not quite usable yet for high frame rate scenarios. But for interactive ones and individual frame rendering, this is absolutely adequate. And with such a system, the overhead for artists is extremely low. There is no need to place reflection probes, set up lightmap UVs, or tune shadow settings. Artists only need to add lights and enable this one-click lighting solution, and they get perfect bounce lighting, shadows, reflections, and anti-aliasing. As you can see, path tracing is definitely the future of rendering. We are very close to see real-time path tracing becoming a reality. Here is a final comparison of all the techniques I've covered. Most of them look fairly similar. They all have pros and cons in terms of quality, performance, baking time, and ease of use. Depending on your own project, one of these might be more adapted to you. For high-end visualizations, path tracing or ray tracing might be your obvious choice. For high-end games, you could use a mix of ray tracing effects and probe volumes. And for mobile applications, light maps will remain the cheapest option. And because Unity is so flexible, you can mix the three techniques together. Sadly for us, this presentation has come to an end. I hope you've enjoyed it. You should now have a better understanding of the lighting in Unity and HDRI. See you next time, and take care.